Hey guys, Andy Robertson here with Greenbelt Academy, and I am so excited for today's lecture where we are going to tackle one of the toughest topics on the Greenbelt exam, and that is ANOVA analysis. All right, let's head over to the computer and get started. Okay, so before I get into the actual lecture itself, you know, we're here at Greenbelt Academy, and I'm teaching about ANOVA because it's included in the Greenbelt Body of Knowledge. But what I also wanted to show is that ANOVA is a topic that's also covered in the Black Belt exam or the CQ exam. And so no matter what exam you're studying for, or even if you're just a college student trying to learn about ANOVA, this is the lecture for you. I'm going to teach this at kind of the Black Belt or the CQ level. So if you can understand today's lecture, you will be absolutely fine in the Greenbelt exam. The other thing I love to tell everybody is stick around to the very end. I'm going to give you a free giveaway specific to ANOVA to help you prepare for the Greenbelt exam, the Black Belt exam, or the CQ exam. No matter what course you're studying for, this free resource is absolutely for you. Okay, let's go ahead and jump into this and get started. Okay, so I want to help. I want to make sure that by the end of this lecture, you completely understand this whole entire idea of ANOVA. So I want to start with the very beginning. In ANOVA, there's a lot of terminology that we use. In fact, this terminology is closely related to DOE. So we're actually going to do an experiment. We're going to start with the design experiment, and a lot of the key terminology that you hear in ANOVA is shared with DOE. So we'll talk about independent variables, dependent variables, factors, responses, levels, treatments, and then ultimately we're also going to talk about the null and the alternative hypothesis. Don't forget, ANOVA analysis is a hypothesis test. So it's important that you understand what your null and alternative hypothesis is relative to the design experiment that you're going to run. Once you understand the basics, we're going to jump into the actual ANOVA process. And one of the most important things that you need to understand with ANOVA is why we use variance, okay? And so there's this idea on the ANOVA table called the mean squares. And so it's really important you understand the relationship between the mean square value and variance, right? So we'll talk about sample variance, we'll talk about the mean square calculation, because you need to understand that mean square is an estimate of variance. Now, that will lead us into the next part of the discussion, which is why do we calculate variance when we're concerned about mean values? When we talk about the null and the alternative hypothesis, our designed experiment really cares about mean values. And so I really want to explain and make sure you understand why we calculate a variance term when what we really care about is things like the population mean. So we'll talk about that. And then we're actually going to do an example. I'm really excited about this because I think an example is the best way to help you understand all of the calculations within ANOVA. There's a lot of, complex calculations, and I want to make sure you understand how these calculations relate back to the mean square value and the data that you collected. So we'll talk about the sum of squares. We'll talk about the degrees of freedom for both the treatment and the error. And then we'll also kind of wrap that up by calculating the mean squares and the F value. And I'll show you how to compare your F-Statistic against a critical F value and make a conclusion on this hypothesis test. And we'll kind of put a bow on this whole DOE and conclude our ANOVA analysis and make an accept predict decision. Okay, let's go ahead and get started. So, like I've kind of already mentioned or kind of alluded to, ANOVA analysis is often the statistical analysis that we do when we've done a design experiment. And usually in a DOE or in a design experiment, what we really care about or what we're trying to assess is whether or not our independent variable has an effect on some sort of dependent variable. And so for the courses of this presentation, we're going to do an example. So the example that I love to do is I love to talk about octane gas. It's a topic that a lot of people understand. And octane gas, right, can be varied at multiple levels: 87 octane, 89, 91, and 93 octane. Now, the question that we're going to explore in our design experiment is, does octane gas impact horsepower? By the way, if you're a car person, I'm going to use fake data. So if you already know the answer to this problem, set that aside for just a second. It's just fake data. I'm just using an example that we are all familiar with. Now, in this specific example, I want to make sure you understand how this problem statement translates into ideas like independent variables and dependent variables. So in relationship to this example, the independent variable is often what we call a factor. In an experiment, we identify factors and we vary them at multiple levels, and we call that the independent variable. You'll also hear it called the control variable. Now, what we care about is the impact that our independent variable has on our dependent variable. So in this example, the dependent variable, which is often called the response variable, is horsepower. We want to optimize for horsepower. We want to maximize horsepower. And the point of the experiment is to determine if changing the octane gas, right, if the octane gas we put in our car has an impact on horsepower. Now, in all of our DOEs, usually what we do is we have a factor and we vary that factor at different levels. So this experiment has 4 levels, 87 through 93 octane gas, and essentially a level is a different set point of a factor. And so this is the way we've kind of designed our experiment. Now, we've got our experiment here. We're going to measure horsepower at 4 different octane levels. And then what we're going to do to make kind of a conclusion on our hypothesis test is we're going to create this ANOVA table, okay? Now, obviously, this table is blank, and so I want to start with the very basics and help you understand just kind of what you're looking at in general. The first box here that we have to talk about are the different variation sources. This is a one-factor ANOVA table. And so when you see the word treatment here, essentially what we're talking about is the independent variable. This is the octane gas. And again, the question that we really care about is, does our independent variable have an effect on our dependent variable? And at the end of the day, the way that we make that decision is by looking at the F value. Now, that F value does 2 things for us. Number one is it tells us whether or not this particular treatment has a statistically significant impact on our dependent variable. Specific to ANOVA, it also allows us to make an accept-reject decision on our null hypothesis, okay? Now, it's really important, too, that before we get into the actual ANOVA process, you understand what the null and alternative hypothesis is for ANOVA analysis. So let's talk about that now. In ANOVA, the null hypothesis, no matter what situation you're talking about, is always the same, okay? And the null hypothesis is that all of your sample mean values will be equal. The mean value of A, the mean value of B, and the mean value of C will all be equal. As it relates to this particular experiment, the null hypothesis could be restated as the average horsepower across all 4 levels will be the same. The average horsepower at 87 octane will equal the average horsepower at 89 octane. They'll all be equal. And that will always be true. That is the null hypothesis in ANOVA. And of course, we can kind of rephrase that in terms of the actual DOE that we're performing. The null hypothesis in ANOVA is that your independent variable, the factor that you're studying, has no impact on the dependent variable, right? All of these mean values will be the same, and the only way that'll be true is if changing the octane gas has no effect on horsepower, okay? That's the null hypothesis. The alternative hypothesis is that at least one mean value will be different than the rest. Now, that could mean maybe 1 level is different, or 2 levels are different, or maybe 3 levels are different. Essentially, not all mean values are equal. Now, the interpretation of the alternative hypothesis in terms of our DOE is that the independent variable has an effect on or does affect the dependent variable. Okay, so now that we have a null and alternative hypothesis, the question is how do we make a decision between those two, right? I love this question. How do we make the accept-reject decision for our hypothesis test? Now, if you think back to statistics, or if you've done hypothesis testing in the past, we're going to use what's called an F value, okay? And you can see it here. You can see the equation here that we're going to use to calculate our F value to make our accept-reject decision. And you can see that it is equal to the mean square of the treatment divided by the mean square of the error. And I want to take a second to really explain this. So in statistics, when we calculate an F value, what we're doing is we're taking a ratio of 2 different variances. The variance at A relative to the variance of B. Okay, we're taking a ratio of 2 variances. You could write this in terms of the sample variance, S squared, which is sample variance, the sample variance of A relative to the sample variance of B. In ANOVA, we simplify this equation into the mean square of the treatment divided by the mean square of the error. And the point I'm trying to make is that the mean square of the treatment and the mean square of the error are both measures of variance. Okay, that's a really important topic. In fact, I want to kind of explain that a little bit deeper here in just a second. You can see here, by the way, on the ANOVA table, there's an entire column dedicated to the mean square. So we're actually going to calculate these values, and then we're going to take the ratio of those 2 values. Now, let me help you, again, just kind of go a little bit deeper here and understand how the mean square is related to variance. So let's imagine I gave you a random set of data, 50 data points, 100 data points, doesn't matter. I gave you a random set of data, and I asked you to calculate the sample variance, okay? The statistical operation that you would perform is this particular equation here. And what you would do is you would take the sum, that Greek symbol there, sigma, stands for sum. You would take the sum of the square differences of each individual value relative to the average. You would call this the sum of squared differences. you can kind of write that as shorthand as just the sum of squares, okay? You would take that sum of squares calculation and you would divide by the degrees of freedom associated with the data set that I gave you, right? N minus 1. Now, I want to take this equation and compare it to how we're going to calculate the mean square. We are going to calculate the mean square of the treatment and the mean square of the error using this equation. Sum of squares, right? You can see that here in the numerator, divided by the degrees of freedom equals the mean square, okay? Now, the reason I show you those two equations is because I want to make sure you understand this point. The mean square calculation, mean square of the treatment, mean square of the error, is an estimate of variance. Okay, it's an estimate of variance. And when we calculate two different estimates of variance, it allows us to take this F value, this ratio of the mean square of the treatment relative to the mean square of the error. Okay, now at this point in the lecture, the most common question I always get is, Andy, you know, the null hypothesis was about mean values. Okay, the null hypothesis was about mean values. Why do we use a variance calculation when what we really care about are the mean values? Okay, so let me explain that now. The way ANOVA analysis works, okay, what ANOVA does is it takes your data and it translates your data into two different estimates of the population variance. Okay, that's really important. Remember, your mean square value, whether it's the mean square of the treatment or the mean square of the error, is essentially a calculation of variance, okay? And essentially what we're going to do is we're going to make these two different calculations for variance, and we're going to ask ourselves a really important question, okay? We're going to ask ourselves this question: does our treatment, our different levels in our experiment, introduce variation into the data set, okay? And I want to relate this back to the null and the alternative hypothesis, okay? If the null hypothesis is true, and you can see it here, right? This is the null hypothesis. If it is true that all of these mean values will be the same, then the mean square of the treatment, which you can see here, any variation between treatment groups could be fully explained by the random nature of the data. In essence, is if the null hypothesis is true, these two values will be approximately equal, okay? They're going to be different estimates. We're going to calculate them differently, but they're both going to come out to approximately the same value because essentially our different treatment groups aren't introducing any variation into the data set, okay? Now, I want to explain these calculations and help you understand how we make these calculations relative to the data that we collect. So I want to run an experiment. This is the best way to learn ANOVA. So here we are. We've got our experiment. We've got 4 different levels, 87 through 93 octane. And for each level in the experiment, we're going to measure horsepower 10 different times. And then here at the bottom in blue, we're going to calculate an average value. So let's do that now, okay? So you can see here, right, you can see we've gone out, we've collected our data, and we've measured an average value for each octane level. And immediately, if you just kind of look at the average values, the way I've created the data is yes, octane gas does have an effect on horsepower. Remember, if you're a car guy and you know this is true or false, throw all that out. I'm just giving an example that we can all understand, okay? Now, the first thing I want you to look at is I want you to look at each treatment group specifically. Look at the actual data points in each treatment group specifically, okay? I want to point out something important. There is variation from data point to data point within each treatment group, okay? 179, 183, 180, 181, 190. There's some natural variation associated with the horsepower measurement. 178, 173, 172, 168, 167. There's variation within a treatment group, okay? And ultimately, at the end of the day, when we calculate the mean square of the error, right, the mean square of the error, essentially what we're doing is we're creating an estimate of the population variance based on the variation within each treatment group, okay? So when we perform this calculation, the way that we work the math is we're going to compare each one of these data points against the average value for this particular treatment, okay? And this is one estimate of the population variance, again, based solely on the variation within each treatment group. Now, that's one way to estimate variation. The other calculation that we're going to make is we're going to look at the variation between treatment groups, okay? So this is variation within a treatment group. There is variation between different treatment groups. And we're going to take these differences, we're going to take this variation between the treatment groups, and we're going to make a second estimate of the population variance. This is going to be called the mean square of the treatment. And that's exactly what it is. The mean square of the treatment is an estimate of the population variance based solely on the variation between the treatment groups, okay? Between the treatment groups. Now, I want to make sure you understand, again, I want to go back to how are we going to make an accept reject decision. So here is our null hypothesis, right? Remember, this all goes back to the null hypothesis. Originally, we assumed the null hypothesis was that the average value at 87, the mean value at 87 would be equal to the mean value at 89, and it would be equal, they would all be equal. All the mean values would be the same. Now that we've looked at the data, we know that that's not necessarily true, right? We know that changing the octane gas affects horsepower. We know that the null hypothesis is false. The question becomes, how do we come to that conclusion using statistics, using data? So here's how we do it. We can make a statistical conclusion regarding our null hypothesis by comparing these two different estimates of variance. We're going to calculate an F value or an F statistic that is essentially a ratio of these two different estimates of variance to determine whether or not our null hypothesis is in fact true, or in this case is actually false. Make sense? And by the way, I know you've already seen the data and you know that the null hypothesis is false, but I want to make sure you understand whether the null hypothesis is true or false. How would this look if you graph the data visually? So I wanted to take that previous data set and I wanted to kind of create some normal distributions here to help you understand these two different estimates of variance that we calculated. Make sense? And I want to relate this data back to the null and the alternative hypothesis. So if we go back here, right, we have 87 octane gas, 89, 91, and 93 octane. And again, there's two different ways to estimate variation. We can calculate variation based on variation within each treatment group, and we can also look at the variation between the treatment groups. Now, in this particular example, we already know the null hypothesis is false. We know that changing octane gas changes the horsepower, okay? And I want to make sure you understand what that means for the actual F calculation, the actual F statistic. If and when your null hypothesis is false, your mean square of the treatment, your treatment variation, right, the variation between treatment groups, will be much larger than your error variation. And that's your variation within each treatment group specifically. And when the mean square of the treatment is much larger than the mean square of the error, what that means is that at the end of the day, your F value will be a large number, okay? When the null hypothesis is false, your F statistic or your F value will be a large number, okay? Now, think for a second. Imagine for a second the null hypothesis is actually true, okay? Imagine that here's our null hypothesis and all the mean values are approximately equal. Assume the null hypothesis is true. If that were the case, then the mean square of the treatment, right, the variation between treatment groups, could be fully explained by the random nature of the data. Remember, when we collected data within each treatment group, 87, 89, 91, 93 octane, there was a little bit of variation from data point to data point. And again, if the null hypothesis was true, you could see some slight differences between these mean values, but on average, approximately, they would be the same. And the estimate of variation that we calculated for the mean square of the treatment could be fully explained by the randomness of the data or the error within the data set. And in this situation, again, when the null hypothesis is true, our F statistic is approximately going to be equal to 1. The mean square of the treatment will be equal to the mean square of the error, and this ratio will be approximately equal to 1, okay? And when we get to the end of the presentation, I'll circle back to this particular conclusion and remind you of these two scenarios. Okay, so let's now actually talk about how you would calculate the mean square of the treatment, the sum of squares of the treatment, and the degrees of freedom of the treatment. Here's the equation for calculating the mean square of the treatment. In terms of the ANOVA table, your mean square of the treatment goes right here, and it's equal to the sum of squares of the treatment divided by the degrees of freedom. Here is the equation for calculating the sum of squares of the treatment, okay? And remember, when we say treatment, we mean the variation between the treatment groups. That's what the word between means. The way we calculate that is we take a sum of average values relative to the grand mean. So I haven't yet explained the grand mean. It's essentially an average of all your data points. And what we're doing here is we're comparing our treatment means against the grand mean to essentially measure the difference between those two values. The way you would calculate the degrees of freedom for your treatment is A minus 1, where A is the number of levels associated with that factor. In this experiment, we had 4 different levels to our experiment, so at the end of the day, our degrees of freedom will be equal to 3. Now remember, when we calculate the mean squares of the treatment, what we're really trying to estimate is the variation between our different treatment groups. Okay? And again, if we look at the data set here, right, here's the data. The calculation that we're doing when we calculate this sum of squares of the treatment is, again, we're taking these sample mean values, these treatment means, relative to some sort of grand mean, right? What is the overall difference between each treatment group on average relative to the grand mean? And in this particular data set, the sum of squares is equal to 1,831, the degrees of freedom is equal to 3, and the mean square is 1,831 divided by 3, which is equal to 610. By the way, if you want to see all of the calculations behind all this, part of that giveaway at the end of this lecture is going to be the Excel file I use to do all these calculations, so you can see all the math in Excel that I use to actually come up with these values, along with a practice exam and a cheat sheet and all sorts of stuff that'll help you on the Greenbelt exam or the CQ exam. Anyways, so that's the mean square of the treatment. It's a pretty simple calculation. We can do the same calculation for the mean square of the error. That's the next calculation we have to make. And essentially, it is the sum of squares of the error, right? The sum of squares of the error divided by the degrees of freedom. Now, here's that calculation for the sum of squares of the error. And again, what we're doing here is we're comparing each individual observation against the mean value from that treatment group, okay? And I want to go back to the data set here to make sure you understand this calculation. For example, we would compare 185.3 against 187.5, 189.7 against 187.5. For these data points, we would compare each of these individual values against the treatment average, 182.2. Same thing here, we'd compare all of these values against this treatment average, and then same thing here for 87 octane. And all of that is intended to make sure that this estimate of variation only captures the variation within each treatment group specifically, right? And again, pictorially, if you look at these these distributions, we only want to just estimate the variation within each individual distribution itself. Make sense? Okay, and then in terms of the degrees of freedom, right? The way we calculate the degrees of freedom is this particular equation, A, which is the number of treatment groups in our experiment, times n minus 1, where n is the number of samples per treatment group. In this particular example, right, we had 10 samples per treatment group, so 10 minus 1 is 9. 9 times 4 is 36, and that is our degrees of freedom here. You can see it. I've kind of plugged this into the table. 148 is the sum of squares. If you work this calculation for this data set, 148 is the sum of squares, 36 is the degrees of freedom, and our mean square value is 4.1. That's 148 divided by 36 is equal to 4.1. That is the mean square of the error. Now, before we calculate the F value for this particular situation, we have to talk about two other data points. The first is called the total sum of squares, okay? So the total sum of squares, there's different ways to calculate this, but the total sum of squares is equal to the sum of squares of the treatment plus the sum of squares of the error, okay? You can also calculate this using your raw data. You can take each individual data point in your sample, compare it to the grand mean, square it, and then take the sum of that. That calculation will give you the total sum of squares. Again, the other way to do it is to simply say 1,831 plus 148 will give you the total sum of squares of 1,978. If you're looking at an ANOVA table, the total sum of squares at the bottom of this column will essentially be the sum of all of these individual sum of square values. That same concept is true for the total degrees of freedom. So again, here at the bottom of every ANOVA table is a total degrees of freedom. It's a really simple calculation to make. One way to calculate it is to say it's the degrees of freedom of the error plus the degrees of freedom of the treatment. The other way to calculate it is to say that it is big N minus 1, where N is the total number of observations in your entire experiment. For our purposes, we had 40 total samples, right? Big N was 40 for us. So we could plug that back into this first equation here, and we could say our total degrees of freedom is equal to 39, right? 40 minus 1 is 39. Or we could say it's 3 plus 36 is also equal to 39. That is our total degrees of freedom, and we can plug it into our ANOVA table. Now that we have all this information, we can calculate the F value for this particular experiment. Now remember, your F value, or your F statistic, is the mean square of the treatment divided by the mean square of the error. And so for us, we can take 610.2 divided by 4.1, and we can calculate an F value of 148.8, okay? Now, remember, that's a big number, and we should probably be rejecting the null hypothesis, which we will do. But in a normal situation, you have to ask yourself, relative to this F value, how do we make an accept-reject decision for our hypothesis test? And we do that by comparing this F value against a critical F value, okay, a critical F value. Now, before I show you the critical F value, I want to remind you of something, okay? When the null hypothesis is false, and I know I'm kind of repeating myself here, but when the null hypothesis is false, the mean square of the treatment will be much larger than the mean square of the error. What that means for your F statistic is that it will be a large number, right? When the variation between treatment groups is much greater than the variation within a treatment group, that ratio is going to give you a really large number, okay? And that's true in our situation. When the null hypothesis is true, the mean square of the treatment can be fully explained by the random nature of the data. Essentially, this F value will be equal to 1. The reason I repeat myself, the reason I tell you that is to make this really important point. When we do ANOVA analysis, we always perform a right-tail test. And the reason that we do that is because we want our rejection region, right? Our rejection region should capture large F values, okay? And we want to capture large F values so that we can reject the null hypothesis when it is false. Remember, when the null hypothesis is false, we are going to have a large F value. And when we have a large F value, that large value should fall into our rejection region, meaning that when we do ANOVA, we should always perform a right-tail test. And so again, if you're looking up the critical F value for ANOVA analysis, you're always going to do a right-tail test because that aligns with our null and alternative hypothesis. Make sense? Okay. So remember, in this particular instance, our F value or our F statistic is a really big number. It's 148.8. And the question becomes, do we reject the null or accept the null? And we have to do that by comparing our F statistic against what we call the upper critical value or the right tail critical value of the F distribution, okay? And this is how you write that statistic mathematically. The F statistic at a specific alpha level, and we're gonna pick 5%, relative to 2 degrees of freedom 1 and degrees of freedom 2. Now, when you're taking the F statistic, degrees of freedom number 1, right? That's what degrees of freedom number 1 is, the degrees of freedom associated with the numerator. Now for us, that's the treatment. Remember, the numerator is the mean square of the treatment. So the degrees of freedom here that we use is equal to the degrees of freedom of the treatment, okay? The second degrees of freedom that you have to know is the denominator degrees of freedom, okay? And for us in our particular experiment, our denominator degrees of freedom is equal to the degrees of freedom of the error, which is equal to 36, okay? So again, we're looking for the F value at a 5% significance level at 3 and 36 degrees of freedom. Here is actually what the F distribution looks like at the 3 and 36 degrees of freedom. Now, you can look up your critical F value at 5% significance level. You can calculate it in Excel. You can look it up on the NIST website. But when you look it up, the critical F value that forms the rejection region of our hypothesis test is 2.866, okay? And I've shaded that in red here. Any F statistic greater than 2.866 would mean that we have to reject the null hypothesis. Now, in our particular case, our F statistic is huge. It's 148.8. It's way off the slide. It's way off to the right. And in this instance, because our F statistic is greater than our critical value, we must reject the null hypothesis in favor of the alternative. Octane gas does have an impact on the horsepower of our vehicle, and the data proves it. That is the entire ANOVA process. That's how you do it. If you're looking to learn more about ANOVA, or you're preparing for the Greenbelt exam or the Black Belt exam or the CQ exam, go to greenbeltacademy.com/ANOVA. I've got a free giveaway. It'll include the Excel spreadsheet where I do all these calculations, a practice exam, as well as cheat sheets with all the equations that you'll need for the Greenbelt exam or the CQ exam or the Black Belt exam. It's everything you'll need to be prepared for those exams. That website also has a ton of other resources, study plans, cheat sheets, other practice exams, a ton of other stuff to help you on your journey to become a Greenbelt. I also have a completely free course. Go to greenbeltacademy.com/free course. I cover the top 10 topics on the Greenbelt exam. These same topics are covered in the Black Belt exam, or they're covered in the CQ exam. And that course comes with video lectures, practice exams, downloadable PDFs that you can take into the Greenbelt exam with you. So if you're serious about becoming a Greenbelt, definitely take advantage of that resource. One last thing, if you really enjoyed this video, do me a favor and hit that like button. That way other people like you can find the same content and grow. And if you're really serious about becoming a Greenbelt, hit that subscribe button. That way, as I publish new content, you get notified and you can stay on that journey of growth and development and learning and ultimately pass the Greenbelt exam. Anyways, I hope you enjoyed this. Thanks so much, and I will see you in the next video. Thanks so much. Bye.